Assalamualaikum warahmatullahi wabarakatuh. My name is Zaidatul Hani binti Zulkarnain and I am the third member of this group. So I would like to introduce our group project and the problem statement. The constant strain triangle element, commonly referred to as the CST element or T3 element in numerical mathematics, is a form of finite element analysis element that is used to approximate the exact solution of a given differential equation in a 2D domain. The reason to call it as constant strain triangle is because the strain is constant throughout it. For the shape of element constant strain triangle, it is simple to create a triangular shaped element, which can be used to represent irregular boundaries. One of the first elements that was frequently employed for continuum stress analysis was the triangle element with three nodes. As we learned throughout the topic of CST, we know that the constant strain triangle consists of 2 degrees of freedom per node. Nodes are numbered in counterclockwise direction and any point within the element are known as displacements u and v, which u is displacement in x-axis direction and v is displacement in y-axis direction. The global coordinate for the constant strain triangle element is x and y. So our problem statement is we are given the model plate that symmetrically in both horizontal and vertical axes, which we need to analyze it with the appropriate boundary conditions. We need to know how to derive theoretically all the parameters needed in this project such as displacements, strains, stresses, stiffness matrix, and also traction force vector. There are two finite element analyses that need to be performed, which are analyzed using finite element method software and also analyzed manually. The finite element software that we need to use is ANSYS, while for the manual analysis, we need to use optics. We need to analyze the minimum of 12 triangular elements on the quarter model of the plate and identify all the boundary conditions present on the element. The results of the two analyzations need to be verified and compared to see whether there is a discrepancy between the two approaches or not. All the difference in results should be taken into account to make sure that this project is valid by justification.
Selamat sejahtera, my name is Go Jessie, and now I will continue to present about ANSYS analysis on the notch template. First, we'll look at the geometry. Since the plate shown in the figure 2 is symmetrical in both horizontal and vertical axes, the analysis can be done by using a quarter model. As you can see from the slides, we are doing the ANSYS analysis on the two-dimensional quarter finite element model for the notch template. Next, the dimensions used in this project is as shown in the slide. In our project, the given value of R over D is 0.3 and the W over D is 1.5. Therefore, we calculated and assumed the dimensions for a quarter model are the W 375 mm and so on, as we can refer from the slides. So after we have generated the quarter model, we can generate the mesh which the two-dimensional region is divided into constant strain triangles. The figure in the slide shows that the two-dimensional quarter template is discretized into 14 CST elements with 13 nodes. Each element size of CST triangles is 160 mm. Next, the boundary conditions and point loads has applied to the specific place, which the frictional support are added to the bottom edge and side edge here, and a force of 5,000 Newton were added at the bottom right edge. Okay, furthermore, we'll look at the results part. For the results part, we can see from the slides, these are the results that we get from generating the ANSYS which we get the component x component, y component deformation, shear stress, shear strain, and we tabulated all the results into these following tables, which we choose 3 points, which is the point A, point B, and point C. The point A, point B, point C, um, you can refer from the slides from just now. Okay, then we continue the analysis for further results improvement by using ANSYS also. We determine the optimal number of elements by try and error, and we found out that the optimal number of elements is 59 elements, and where the size of each triangle element is 80 mm. The optimal number of elements is determined by refining the mesh until a critical result, such as the displacement value in specific location, converges, meaning that it doesn't change significantly as the mesh is a refinement. So we can see from the following slides, these are the tabulated data that we found that the total displacement that does not change when we change the CSD size. So after we do the result improvement by using the optimal number, we get also different value for the displacement and also the normal stress, normal strain, shear stress, shear strain. These are the results that we tabulated it. So this also the results. Okay, so for the discussions, we compare the results between 14 CSD element and also the optimal number, which is the 59 CSD. We found that the displacement between these two, the displacement value, the shear stress value, the shear strain value are different between the results for this 14 CSD and also the optimal number, which is 59 CSD elements. This is because in the problems where the stresses changes widely over an area, such as in notch template, it is a good practice to decrease the size of elements, the CSD elements in that area to capture the stress variation. Therefore, the optimal number of elements will give more accurate results than the 14 CSD elements. This proves that and suggests that the smaller elements will better represent the distribution. So that's all from me. I'll pass to my friend to continue next. Thank you.
Warahmatullahi wabarakatuh. My name is Nashami binti Zamran. Today I want to present about manual analysis. We use the octave to determine the manual analysis. In the question, we need to find the displacement for point A, B, and C. And based on the result that we get in the octave, we need to compare in with the ANSYS result. Okay, for the ANSYS result, for point A, the displacement is 0 and point B is 2.77 exponent negative 3 and for point C is 1.47 exponent negative 2. This is the result in the octave. This is the all the displacement that that has been determined. Okay. For the octave result, for the point A, we get 2.8133 exponent negative 7. For point B is 1.6967 exponent negative 6. And for the point C is negative 9.8778 exponent negative 7. So, as you can see, there's a huge difference result between the ANSYS and the octave. Okay. And then I used to calculate the percentage error. Percentage error for point A is 100%. For point B is 63.26% and for point C is 248%. In based on these three notes, for point B is the less percentage error. Uh, percentage error. So we get the huge number of error because it might have a error when we combine the global matrices because we combine it by manual calculation. So it might be some error when we put the k based on row and columns. Uh, it, it is because it huge metric 24 by 24, so it might be confusing when we put the k in the column and row. So the solution for to get the less error in the octave, we can use the function to determine the global matrix. I think that's all for me. Thank you.
Lastly is conclusion. In a conclusion, the objective of this project to verify and compare the results of finite element methods, which is constant strain triangle on notch template with a minimum of 12 triangular elements using manual analysis, which is octave, and software analysis, which is ANSYS, has been achieved. The main comparison that we analyze in this project is all unknown displacements for point A, B, and C. Moreover, we also did some discussion on how to improve the further results by using ANSYS. As we use 14 elements for the first analysis by using ANSYS, we need to improve it by the optimum number of elements, which is 59 elements. It shows that the results of optimal number of elements, which is 59 elements, which the sides of each triangle elements are 80 mm, is more accurate than of the 14 elements which the sides of each triangle elements are 160 mm. Lastly, we compare the value of stress concentration between theoretical and calculated using the formula of stress concentration equal to stress max over stress zero, where stress max is from finite element method analysis, while stress initial is from the equation of F over T times T, where T is the plate thickness. The stress concentration of calculated is higher than the stress concentration of theoretical. It produces large percentage error, which is 60.19%. There might be some errors occur when analyzed using the ANSYS software. The way to improve the analysis and eliminate the discrepancies is to decrease the size of CSC elements to increase number of elements to get a better and more accurate result. That's all from me. Thank you.